I could not remember if we were the third one or the second. Yeah. Usually one. The fourth one, no. Yeah, okay, okay.
So, welcome to this semester seminar. I'm very glad to have our three postdocs here in Rolla present their work, namely George Bougas from my group, Hastiko okay, from SUNS, and then Yang Cheng from Harvard. Yeah. So we will have two AMO talks and one AMO talk and two astrophysics. Yeah. Okay. So first we will start with George Bougas and we will hear about signatures of turbulence in driven dipolar quantum gases. So stay with George. Thank you very much.
All right. Thank you very much. I hope you can hear me correct. I'm going to talk about turbulence. In dipolar gases. So turbulence, it's a complex phenomenon that has a large history.
That's okay.
Okay. It's recording, right? So I'm going to talk about turbulence. So turbulence is a complex phenomenon with a long history. So here you see a painting by Leonardo da Vinci. And on the right, you see one of my simulations. Now, there is, of course, a big jump between this group. And in the remaining few minutes, I will try to explain everything that goes in between. So, one example of turbulence is when we think of a fluid as an obstacle. And in that case, we can have some vortices going beyond the fluid. And at the very end, we have like a turbulent flow, right? And if the gas goes at a very high speed, you will have this turbulent regime. Now, turbulence occurs also at larger scales, on the scale of planets, where essentially you have like zonal jets. For instance, here is like a famous example of Jupiter, but you can also encounter that on Earth. And this plays a role because you can transfer energy inside the system, inside the planet, and it plays a huge role because it can affect the climate of the planet, for instance. But you can go also to larger cosmic scales. And there you have, like, for instance, plasma, where again you have transport of energy through turbulence, and this plays a role, for instance, in transformation. All right, so these are some examples, but I didn't say to you about what is turbulence. And this is quite complicated, actually. It's a non-equilibrium phenomenon, non-linear. It occurs in aerodynamical setups. Typically, and there is energy cascade from large to small length scales, or vice versa. So this is the most important part is that it's a nonlinear phenomenon, so it's quite complicated, dynamical nonlinear system. And there is also, this means that we have to track many degrees of freedom, right? There's an energy cascade across many length scales. And it's a nonlinear, and we also need to solve like aerodynamical setups, which means we were talking about fluids, that we have to deal with Navier-Stokes equation. And this is already a very bad start. But, however, there are some cases where you can resort to statistical description and you can understand turbulence in some particular setups, right? And I'm going to talk about the, like one of the most significant, let's say, results, which is the non-equilibrium steady state, where essentially you take now the distribution of energy or momentum space. There is this non-equilibrium steady state where you have an injection of energy at some large length scale, essentially. which flows all the way down to large momentum, meaning small length scales. And in this regime called the inertial rings, there is like a power law behavior, which is independent of the characteristics of the system, right? This is like a universal characteristic of fluids. And then you go all the way down to dissipation, right? Because we were talking about aerodynamics, this can be like viscosity. So you go all the way down where the energy is dissipated through viscosity. And this is, there is a power law behavior in this inertial range, and the exponent gamma actually depends on the physical mechanism, right? It's not something fixed. And now there are some important mechanisms. It's, for instance, vortices, as we have seen in the fluid, where we have like large vortices which go down to smaller and smaller and smaller, and then energy is transported through them. And then you can have also like waves mixing non-linearly, which is another way of transporting energy across many length scales. All right. Now, so far what I have been talking to is classical, right? But turbulence has been actually observed in quantum systems, in quantum general gases. And one can ask the question, okay, why should we complicate our lives even more? And it's already a complex phenomenon. Why should we go to a quantum regime, right? But I will try to explain why, first of all, you observe turbulence, and second, why it's somehow important to observe this in quantum gas. So, for instance, here you see a profile of the quantum gas, and you see like vortices appearing on the left figure, which is a precursor of vortex turbulence. And on the right, you see like this power law behavior, and the exponent actually is related to wave turbulence, with wave turbulence. All right, so first of all, why does turbulence occur in quantum gases, right? That's one question. And if you take a gas, like at normal temperature, then you have particles swimming around back and forth with some velocities. But every particle, if you start lowering the temperature, and if you think quantum mechanically, every particle is a wave, right? It has a wave attached to it. So, and if you think about the wavelength, this goes, which is inversely proportional to temperature. As you keep lowering the temperature, then the wavelength becomes more and more large. And at some point, this is going to be like a huge wave, and actually it goes around all the particles, right? So if the wavelength is larger than the distance in the particles, and eventually the wave functions for different particles are going to overlap. So now we're talking about one giant wave. Right? And if we're talking about bosons, an ideal boson gas, this is like the onset of boson condensation. However, even if we talk about small interactions, you can still describe the entire system with a macroscopic wave function, a single wave function. And you can see here actually that the wave function is connected with the density, right? It goes to macroscopic observables. And if you do this decomposition, you can assign a velocity to the gradient of the phase. And it turns out that the equations are actually similar to the velocity field of the fluid with zero viscosity. And that is called the superfluid, right? Because it doesn't have viscosity. So if you take a bucket, you have a gas. You rotate the bucket, the gas stays still because there is no friction to fall with the bucket, the walls. All right, so now why should we care, right? I mean, why should we go and study turbulence in this regime? So the important stuff is that there is quite good controllability in these setups. And this is because with quantum gases, there is the possibility to trap them and image them across many length scales. And if we go back to our non-equilibrium steady state picture, then we can think that, okay, we can essentially save the traps that the particles are in, and then essentially we can control the scale at which we inject energy. And essentially we can control also the scale at which energy is dissipated, because this is essentially the depth of the trap, right? I mean, if you go all the way to very large momenta, these are high energetical particles, and that they can escape from the trap. And by doing so, you can, there's also one additional feature, and that is the control of the interaction strength, right? For short range van der Waals interactions that neutral atoms interact with. And with that, you can now study universal aspects of fluids, which is quite difficult to do with normal fluids. And in this nice paper, for instance, they have validated and further expanded a non-equilibrium steady state, non-equilibrium equational state, where they have connected the flux, essentially the rate of energy which goes through the system, with the amplitude of the steady state, right? And this goes, you see like our law behavior. And of course, you see that for many different interaction strengths, all of the bonds fall on top of each other, right? It's like a validation of this universality. Okay, so of course, I should stress that the quantum fluid is not a liquid, right? It's not a classical liquid, right? Because in our learning, superfluidity should be in alarm for that, right? There's zero viscosity. And for instance, quantum gases can have different phases, right? So, for instance, if you consider magnetic dipoles with long-range interactions, these can have different phases. And now, if you consider like the ratio of dipolar interactions with respect to the short-range interactions, then we can have like different phases. And in panel C, you see like a superfluid that we have been discussing before. But if you keep lowering this interaction ratio, then eventually you will hit what is called the supersolid, which means like you have a with a superfluid background, and on top of that you have a crystalline structure, and it's called the supersolid. And it's very interesting because now you have there's a distinct dynamical response with respect to the superfluid, and this goes back actually to symmetry breaking, because you break two symmetries in this kind of supersolid. And what I'm going to talk about is essentially the impact of a supersolid turbulence, right? How does a supersolid affect turbulent behavior of quantum gas, in particular this dipolar quantum gas? So I'm going to use the superfluid to supersolid transition, and using the tunability of the interaction, the short-range interactions, we're going to go back and forth between these two phases, as is shown in the sketch here. And initially, we start with the supersolid, and we have a cylindrical symmetric trough, and the dipoles are polarized in the direction which points outwards from the plane. Right. Okay, so if we look at the density profiles throughout evolution, then we have like instead like you see pink the background, and then you see like a crystalline structure, right, with a six-fold symmetry. Now, as time goes on, you have perturbations, right, and the symmetry is gradually broken, right, the six-fold symmetry. And then if you go to really large times, you see that you have very significant density modulations on top of the gas. All right. So, of course, this is like, this hints at turbulence, but it's not like important, right? We have to look whether we see this non-equilibrium steady state by looking at the momentum distribution. So, here I plot the momentum distribution, actually. So you have the momentum. Actually, it's azimuthally average momentum distribution, because the Z component doesn't play a role, because it's a quasi-two-dimensional gas. And on top, I have the compensated momentum distribution, because there is a power law, but if you multiply with k to the gamma, essentially you see like a plateau, right, around the value 4. And essentially, the color bar dictates the different time instance. And you see that as time goes on, you have the slope which gradually decreases until you hit the steady state on the plateau, right? So this means that we are talking about non-equilibrium steady state over time. And the exponent, actually the fifth exponent, turns out to be close to 2.8, which is already similar. This alludes to wave turbulence, right? About the mechanism that energy is transported in our system. All right, so this is the signature of wave turbulence in this driven dipolar quantum gases. All right, but now we want to see what is the difference actually between a superfluid and a supersolid, right? And for that, we're going to start with a superfluid also, and we want to look at the exponent throughout the evolution time. This is the effect exponent for many time instants. And you see actually that one interesting thing is that the saturation rate is quite different for these two states, right? It seems that the super solid, which is in green, saturates faster than the super fluid, right? And the question is, why does this occur? So within weak wave turbulence, actually the rate at which energy is transferred to large momenta is somehow fixed. There is some universality class. And for instance, it goes like t to the power of beta, and beta is an exponent which doesn't depend on the characteristics of the system, right? It depends on the dimensionality, not on the driving or what kind of means of state we use. And this means that actually even for a superfluid or super solid, the energy is transferred more or less at the same rate. But these two states are actually not equivalent, right? They're not exactly the same. And if we look at the momentum distribution at the initial time instant, then you see that for a super solid, we have a much more extended momentum distribution. And this is because we have a crystalline structure, right? And this crystalline structure, if you go to momentum space, is assigned to a high momentum peak, right? Now, this is a finite size system, which means that we don't have one peak, right? We have higher harmonics, so it's a more extended momentum distribution. And this means that if there is a way from energy is transferred to larger momenta, the supersolid has already a great advantage because it starts at higher momentum, right? So it saturates, there is an establishment of the non-equilibrium state faster for the supersolid than the superfluid. Okay, so this brings me to my summary and conclusions. So we have observed wave turbulence in dipolar quantum gases and driven across the superfluid, the supersolid transition. We have seen that the non-equilibrium steady state is established faster when we start from supersolid, superfluid. And actually, there are many interesting perspectives one can look at. One is to investigate further the turbulent behavior of these driven dipolar gases. And one can make his life even more difficult by going to the more tightly squeezed uncake, where essentially we go into what is called two-dimensional turbulence, where essentially you don't have only a one-sided cascade, but you have a dual cascade, both backwards and forwards. It's more difficult in treatment as well. And of course, if you remember from the phase diagram, when we changed the interaction length, the interaction ratio, there was another phase of the far left, which I didn't talk about, which are more exotic phases. These are called dipolar droplets. And in these regimes, actually, you have beyond near field effects taking place. But also, there is also another possibility to study further the dynamical response of supersolids and understand better their difference with respect to superfluids. For instance, when you introduce some small perturbation into the system, and you study how does this perturbation expand through time. And with this, I would like to thank my collaborators, Josef Mukherjee in Lund University in Sweden, and Simon Smisakid is here. And with this, I would like to thank you also for your attention. Thank you very much.
Thank you very much, George, for the nice talk. So, please, questions.
On the slide where you introduced the super solids, you got a ratio of, I think it was A over A.
Yeah.
What are those variables that go into it?
So A to D essentially is dependent on the magnetic moment of the atoms. It's called the dipolar length, but essentially depends on magnetic moments. And A is the interaction strength of neutral atoms interacting via van der Waals forces. Because if you have atoms, they're neutral, they have van der Waals interactions. And essentially A controls this interaction strength. So essentially, when you have large dipolar interactions over normal interactions, if I may say so, then you have the supersolid character. Because you have like another length scale, which is from the long range interactions kicking in. This is why you have actually crystalline structure.
Yes, please.
So if you're talking about non-equilibrium steady state, so these systems are driven.
Yeah.
I may have missed it, so how are they driven?
So I mean, in our setup, it's only the scattering length, the interaction strength is driven between the two phases. So this,
So that's the only drive that you have.
that's the drive, yeah.
The parameter sweep is the only drive that you have.
Yeah, yeah.
Okay.
But also in experiments, what they do, I mean, to insert some energies, they have a box. I mean, a travel sensor which has a stable box, and then they set the box. And this introduces a large,
Right.
a large scale injection of energy. So it depends, but in our case, it's driven for the
So the
interaction.
parameter sweep.
Exactly.
Any other question?
So I have a quick, maybe stupid question. We don't know what is at the center of neutron stars. It could be superfluids.
Yeah.
Or how would I distinguish superfluid from super solids on a microscopic scale from the equation of state, for example?
Well, that's a good question. I don't know the answer, but
Shape the neutron star.
yeah, exactly. Yeah. That's a large scale injection of energy, right? That's the largest you can get. Okay. No, I'm happy to collaborate.
No, I was wondering if it produces a steeper equation of state or
You mean this power law behavior, right?
Yeah.
So, okay, for instance, okay, if you have a super solid, you have two speeds of sound, right, for perturbations, because you break two symmetries.
Yeah.
So I don't know if that actually can affect, for instance, the behavior of the neutron star. I mean, if it can be actually observed, but I'm not sure. This is just a high speculation.
What's your fault? You put the picture on it.
But on the other hand, on the macroscopic level, the threshold might not be evidence, right? Because it's a quantum. It's a quantum.
But there should be some signature on a microscopic level.
Any other question, please? Be great. Okay, I have just one question then, before we stop. So was the driving between the two phases crucial for finding turbulence or not? Could you do the same within one of these phases?
I mean whether I start from superfluid
Yeah.
or super solid. Okay, so when I start from a superfluid, actually it's not possible. So actually only when I drive the system across the phases you can see that.
Okay. So if there are no other questions, further questions, thank you so much. Now we have Ashley, please.